This is a schematic of what a supercell thunderstorm typically looks like from a satellite perspective. The overshooting top appears like this in the visible imagery. Above anvil cirrus plume corresponds to this region in the visible imagery. If the storm is quite intense, you'll typically have a crisp edge to the anvil cirrus, which looks like this in the visible imagery. Another feature that may appear is the flanking line, which is the boundary between the outflow region of the storm and the inflow region of the storm. One of the features that you may see in the inflow region of the storm are these inflow feeder clouds, which form within converging inflow near the strongest updraft, and they look like this typically in the visible imagery. West of the flanking line, you may sometimes see lines of towering cumulus that form above an invigorated RFD, also known as flanking towers, and they may appear like this in the visible imagery. The orientation of the low-level features of interest does vary depending on storm motion and environmental winds. Most severe storms do not exhibit these storm signatures from satellite. However, when you are fortunate enough to observe them, the storm is most likely severe. Now let's discuss inflow feeder clouds with information from this study. First, they're not necessary for severe weather occurrence. Inflow feeder clouds are an indication that a storm is rapidly intensifying and may produce severe weather soon thereafter. If you observe inflow feeder clouds, keep in mind there is a 77% chance of severe weather within 30 minutes, and if you combine inflow feeder clouds with mesocyclone detection from the MDA, that number goes up to 85% chance of severe weather within 30 minutes. Let's go ahead and look at an example. We see a couple storms that are developing quite rapidly, as indicated by the overshooting top and also by the crisp edge to the anvil cirrus that we see on both plumes. And if we look in the southern flank of both storms, we see the development of inflow feeder clouds. If we go to a little bit later in the life cycle of these storms, you can see that both these storms have robust-looking inflow feeder clouds with low-level clouds moving towards the updraft region of the thunderstorm, like so. We see overshooting tops and above anvil cirrus plumes as well with these storms. For the northernmost storm, near the end of the loop, we begin to see outflow on the backside of the storm and a flanking line develop and moving southward. But with the southernmost storm, we don't see that. We continue to see these inflow feeder clouds to be observed here in the GOES visible imagery. This is Texas and Oklahoma over here from May 16th of 2017. Sometimes cloud streets in the warm sector, like we see over here, can be observed moving into the inflow region of the storm. Note the inflow feeder clouds in the vicinity of the inflow region in this storm, and also with this northern storm over here as well. The clouds appear to accelerate as they approach the inflow region. What about inflow feeder clouds at night? We do not have the high-resolution visible band available at night, but we do have IR bands. Even though they're lower resolution, they are available. So let's look at this case from March of 2020 in North Texas. In the upper right is the 10.3 IR band, and the upper left is the nighttime microphysics RGB. Lower left is the GLM flash extent density, and then the lower right is the MRMS composite reflectivity. We begin with the IR band, and just north of Abilene we have this tornadic supercell that's moving off to the northeast. Just east of Abilene, along the southern flank of the storm, we see some low-level clouds develop, and they don't appear particularly different from some of these other clouds that you see in the scene, so it may not even strike your attention. But if you look at the nighttime microphysics product, you get a little bit more detail. I'll go ahead and draw in the region of interest, And the first thing to note is that these appear to be lines of cumulus that are oriented like so. The orientation is important because with a stronger region of inflow into the storm, you'd expect the inflow coming in like this, so that these cumulus lines are oriented parallel to the low-level inflow increasing into this storm. Also, we see that the clouds are increasing in depth. We're changing colors to these more yellow colors, so they're also growing in the vertical. Note that they're actually just above a region of stratus, this aqua-colored, or actually stratus, that's in the vicinity. The lightning down here from the flash extent density field shows an uptick right around the time that we see the occurrence of these inflow feeder clouds as well. Next, let's go ahead and zoom in to the nighttime microphysics product, and if we look just east of Abilene in this region, you can see again the orientation of these indicating that they're likely inflow feeder bands because they're parallel to the low-level wind direction that would be feeding into the storm. You can see them develop in the vertical, and also we have 1 minute imagery here to work with. These bands actually developed right around 640 UTC, and they were pretty robust by about 655. Within a span of about 10 to 15 minutes, these bands became detectable here, and it means that the 1 minute imagery is actually crucial for being able to identify this. I'm not sure if you would have been able to pick this up by looking at CONUS scan, because you would have just had a few images to look at. The 1 minute data was really crucial. So in summary, inflow feeder clouds may be observed at night. You'll probably have a little better success with these by looking at the nighttime microphysics product compared to looking at an IR band. And you do need a little bit of luck. Imagine if some of these higher clouds that we observed here were a little further to the north. We would not have been able to see this. Now let's talk about lines of towering cumulus that develop above an invigorated RFD. The information I'll present here is from this study, where they referred to these signatures as flanking towers. Like inflow feeder clouds, these are not necessary for severe weather occurrence. There's less research compared to inflow feeder clouds on this topic, possibly due to being much less frequently observed. What mechanisms cause these to develop and how they relate to supercell behavior is an area of open research. However, what we know at this time is the signature indicates that the supercell is undergoing intensification or near peak intensity. If we look at our example over eastern Colorado in a situation with northwest flow, you can see many indications of a severe storm here. We have overshooting top, we have an above anvil cirrus plume emanating out in this direction. The edge of the anvil cirrus is very crisp, and finally on the west side or upshear flank of the storm, we notice this signature right here. So these are the lines of cumulus that form above an invigorated RFD, also known as the flanking tower. Note that we do not see inflow feeder clouds where we expect them to on the southern portion of this storm. One other thing to note is near the end of the loop, you can see this arc that comes out from the thunderstorm. That's actually the outflow boundary emanating out away from the storm. As for limitations, keep in mind that most storms will not exhibit these satellite observed signatures. Of the storms that do have these signatures, there are a variety of reasons why you may be unable to observe them from satellite. For example, cloud obscuration, for example, from other nearby anvil plumes. Nighttime is another reason you're unable to use the high-res visible band at night. Dust and smoke is a common obscuration source as well. Also, if you're looking at low-top supercells, everything is smaller and it can be quite a bit more subtle to observe these with low-top storms. Next, I'll talk about the enhanced V signature, which we see from IR imagery. There's been a lot of studies on the enhanced V. I'll highlight a couple of them at the top. But the signature that we're looking for is relatively warmer brightness temperatures that exist immediately down shear of the overshooting top, with colder brightness temperatures on either side to form a V shape. Notice that both of these storms, I highlighted the V shape with these dashed lines, and both of these storms have an enhanced V signature. If we continue on here, what we can conclude from past studies is that the storm is most likely severe. We cannot conclude a storm is non-severe in the absence of the enhanced V. In other words, it's not necessary for severe weather occurrence, much like the inflow feeder clouds and the invigorated Here's GOES 16 IR 1-minute imagery over North Dakota, and we can see a couple different storms that exhibit the enhanced V signature. One of the things that you can look for in terms of quantitative information from the enhanced V signature is the brightness temperature difference between the overshooting top and the warmer brightness temperatures that you see immediately downwind of that. The westernmost storm has a brightness temperature difference of 18 degrees Celsius, and this easternmost storm has a brightness temperature difference of 11 degrees Celsius. A brightness temperature difference of approximately 15 degrees Celsius is an approximate threshold between severe and non-severe storms that exhibit an enhanced V. Higher brightness temperature difference values would increase the probability of the storm being severe, with higher end values in the 25 to 35 degrees Celsius range. In summary, if you do observe the enhanced V signature, make use of it in your warning decision-making process.